Hello, today I want to talk about section 10.1. This is an introduction to sequences and series, and it's actually going to be a reminder that we've seen some of this before. So we saw some of this in Calc 1 when we talked about Riemann sums. And then you've also seen this as far back as elementary school. So when you talk about sequences, a lot of times that's actually done in elementary school. And I'll show you sort of maybe where you have seen it and hopefully jog memories about some of the stuff that we're going to go through. So a sequence is an ordered list of numbers, and it's going to take the form A1, A2, A3, and so on. It can be finite or infinite. Usually we're interested in infinite ones. And in particular, that's the ones that you actually would have seen in an elementary school setting is actually the infinite ones, which is kind of weird, but you don't call them infinite in elementary school, but they go on forever. You can continue adding terms to this sequence of numbers, and that's what we would ask of you to do, right? So we're usually interested in these infinite ones. Importantly, they're ordered. So there's a first term, a second term, a third term, a fourth term, a fifth term, and they appear in that order. So you can't rearrange them and have the same sequence. So the sequence changes if you've rearranged them. So in elementary school, the thing that we ask you is, what's the next number in the sequence? Or what's the next two numbers in the sequence? That's the kind of thing you're asked, and that's the kind of thing that you're able to do at that point. So 1, 2, 3, 4, the next number is 5, and then 6, then 7, then 8, and so on. 1, 3, 5, 7, 9, those are all odd, so the next one is 11. The next one's a little trickier, 4, 7, 10, 13. You stare at that for a second. Difference of 3 between each of them, probably 16 is the next one, then 19, and so on. The next sequence starts the same, 4, 7, 12, 19. Now notice that those two are different sequences. And so even though they have two of the same number, they're sort of diverge from each other, they change. 4, 7, 12, 19. So what's the next number going to be? No? So you can kind of do this a couple different ways. So the difference between the first two is 3, then 5, then 7. So 9 is going to be the next difference. So it's 18, or 28, excuse me. 28 will be the next number. Or you can actually sort of think of this and say, okay, so 4 is 1 squared plus 3. 7 is 2 squared plus 3. 12 is 3 squared plus 3. 19 is 4 squared plus 3. So the next one will be 5 squared plus 3, which is 25 plus 3 is 28. And it's actually the same thing as what you got before. So this is kind of one way that we do prove some certain facts is we think of something in two ways and then equate the two. Say, oh, that's actually the same. They're the same numbers as we get before. So that's kind of neat. So what that kind of tells me here is the difference is odd numbers if the numbers are being squared. So that's kind of crazy. So the difference of two squares is going to be an odd number. Okay, that's kind of cool. All right, so that's the kind of thing we would ask you in elementary school. What are we going to ask you next? So next you kind of move on and you go into middle school and then high school. Probably nobody remembers middle school. I don't remember middle school. It was one of those traumatic times, right? So, but we do learn the next question. And the next question might be, what is the 90th term in this sequence? That's a harder question, right? And it's a question that you could technically figure out by listing the thing 90 terms out. But most likely, well, and what we wanted you to do as a high school student was to start thinking like a mathematician. And this is not to be said in a like a complimentary way necessarily, but we want you to get lazy. It's essentially the thing, right? So as a mathematician, I look at this and I say, I don't want to do that. I'm too lazy for that. Instead, what I'm going to do is I'm going to figure out a formula, a function that describes the n term, any term in my sequence, and then put 90 into that n. So that's what we expect from this one. So in this case, let's start with the first one. So I'm talking about odd numbers. And so if I think about odd numbers, well, so there's a formula for the odd numbers. How do I do it? I'm going to say it's probably what, 2 times n. So what I will do here is I will list out n as being 1, 2, 3, and 4, first, second, third, and fourth term. And then I'm going to say the first term is 1, the second term is 3, the third term is 5, the fourth term is 7. And so it turns out it's going to be 2 times that minus 1. So 2 times 1 minus 1 is 1. 2 times 2 is 4 minus 1 is 3. 3 times 2 is 6 minus 1 is 5. 2 times 4 is 8 minus 1 is 7. And so what I would get here for the 90th term is 2 times 90 minus 1 is 180 minus 1 is 179. So 179 is the 90th odd number. That's kind of cool. What's next? Next, we talk about 1, 2, 3, and 4 again. This time I'm talking 4, 7, 10, and 13. And so I say, okay, so how do I get between these? It's a difference of 3 between each of the terms. And so I think, well, that's n plus 3. And that's going to be 4. N plus, or 2 times 3 plus 1 is 7. 3 times 3 plus 1 is 10. 4 times 3 plus 1 is 13. So it's going to be n times 3 plus 1, or really 3n plus 1. So the 90th term in here is 3 times 90 plus 1. And 3 times 90 is 270, so it's 271. So 271 is the 90th term in that sequence. And then the last one I actually did a little bit already. So I said it was going to be 1 squared plus 3, and 2 squared plus 3, and 3 squared plus 3, and 4 squared plus 3, and so on. So I get n squared plus 3. So what I get here is the 90th term is 90 squared plus 3. And so what am I going to get? Well, 90 squared is 8,100 plus 3. So 8,103 is the 90th term in that sequence. Okay. So what we've kind of danced around here with this terminology is we need to talk about two forms of these sequences. So the first form is what we call a recurrence relation. This says that I can determine any term in my sequence by what happened before. And so if I look at my thing here, I have 1, 2, 4, and 8. So each term is 2 times the previous term. So the way I write that is that the n plus 1 term is 2 times the n term. So 2 times the previous term. And then if I do that, I have to give you a starting point. I say the first number you have is 1, and then you multiply by 2 each time to get to the next one. Okay. Now this is not as useful as what we had on the last slide, right? So the last slide, we ended up getting what we call a closed form of the sequence. This is a recursive form of the sequence. There are times when I can go between the two. There are times when it's difficult to go between the two, and a very sort of famous, infamous one of these you will have probably seen. 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. So this is what's called the Fibonacci sequence. And the Fibonacci sequence starts with 1, then it's 1, then it adds the previous 2 to get the next one. So 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, 8 plus 5 is 13, and so on. And so you add the previous 2 to get the next one. So this is a recursively defined sequence. It's going to be an plus 1 is the last term plus the term before it. And I have to give you 2 terms, A1 and A2 here. They're both 1. Okay. And so we can say, okay, so that's great. So is there a nice closed form for this? There is. Well, I shouldn't say that. There is a closed form for it. It is not nice. So the closed form for the Fibonacci sequence ends up having some sort of weird but beautiful structure to it. And so I will show you this thing. So the closed form for the Fibonacci sequence, yeah, it has some pretty nasty stuff in it. It has square roots of 5 in it, which is kind of interesting. So here is the closed form of the Fibonacci sequence. So the nth Fibonacci number, the nth number in this sequence is 1 over the square root of 5 times 1 plus root 5 over 2 to the n minus 1 over root 5 times 1 minus root 5 over 2 to the n. There's like the root of a quadratic polynomial in here. So this 1 plus or minus root 5 over 2 is a quadratic. Powers are n, so that's the thing that you're plugging in to figure out which term you're looking at. And then I've got a root 5 in the denominator of each of those. Now this is surprising, to say the least. We end up getting nice integers out of this function. No matter what n you plug in, you get an integer out, because there are no square roots of 5 in the Fibonacci sequence. So it's surprising and kind of nice, actually. It's kind of interesting that this function actually outputs only integers when your inputs are positive integers. So it's kind of crazy. So we're sort of happy with that. That's great. And we kind of work from there. So for this one, we basically, the kind of takeaway from all this, I guess, you don't have to know how to get between the two immediately right away for every single sequence you're ever given. But for specific ones, we will figure out how it works. So we also have this sort of explicit formula, or it's going to be like the closed form of the sequence. It's going to be a function that you plug the number n into to find the nth term of your sequence. This is actually the goal, as you kind of might imagine things. And in particular, when you talk about limits of these sequences, this is absolutely the goal. You want to find those functions that when evaluated, give me those terms in the sequence. All right. So we can find an explicit formula for most of these things. Basically, kind of how you did it in high school, which is kind of like a really guess and check and try and figure out and see if you can find. You know, it's not a hard set. You do this and it works kind of thing, right? So here I look at this sequence, -2, 5, 12, 19. There's a difference of 7 between each two, and I start at -2. So you might say, well, I can actually do this. I get -2 plus, well, 7 times n minus 1. Again, maybe I have to list n as 1, 2, 3, and 4. And so then I get 7 times 1 plus -2 is 5. 7 times 2 plus -2 is 12, so on. I could then, at this point, evaluate this. So I get -2 plus 7n minus 7. So that's just 7n minus 9. And so n, when you plug it in, 7n minus 9 gives me the term. So 7 times 1 minus 9 is -2. 7 times 2 is 14 minus 9 is 5, and so on. So that's our closed form for the first one. The second one, I kind of look at this and I maybe go through something and say, well, you know what? This is basically 3 times 2, 3 times 4, 3 times 8, 3 times 16, so on. So this is basically 3 times the other sequence that I had above. So the sequence I had above was just 1, 2, 4, 8. Okay, and I can find the closed formula for that, and then kind of multiply it by 3 to figure out the closed formula here. So what I get, so the 1, 2, 4, 8 is just going to be 2 to the power, well, n minus 1, because when I plug in 1, I want to get 1. And then I take 3 times that, and that's going to be the closed form of my sequence. Okay. So being able to kind of translate between the two is important. It's something we want you to kind of get some practice at. But it's not like the only thing we want from it. Like I say, it's not always possible in the case of seeing things like this Fibonacci sequence or some other sequences. It doesn't work out as well. All right. The limit of a sequence is written as limit as n goes to infinity of an equals L. And this holds if an can be made arbitrarily close to L by taking n sufficiently large. So basically, if I can get really close to the number L by taking more and more terms in my sequence, the farther along in my sequence I go, the closer I will get to L. That means that I'm going to end up going to L. So this is sort of the limit is going to be equal to L. we say that this sequence converges to L. So converges, meaning it goes to that. And if it does not have an L, if that L is an infinity or something like that, or L is nothing, then that's going to be a divergent sequence. So the sequence diverges if it doesn't have a nice number that it goes to. It converges if it goes to something finite. Okay. I want to point out here that this limit is different than the limit you saw in the very beginning of Calc 1. So the beginning of Calc 1, we had this sort of limit as x goes to infinity of some function is equal to something. Well, those x's can take on any real value as it goes to wherever you want to go. So as x goes to 4, you're talking about things like 3.5 and pi and these numbers that are less than 4 that are going to 4. For us, n is always an integer. So it doesn't make sense for n not to be an integer. I can't take the pith term of a sequence. And so this limit is what I would call like a discrete limit. It is cut in nice intervals of 1. And so it is n is 1, 2, 3, 4, 5, and running as integers up to infinity, not running as real numbers up to infinity. It's a subtle difference, and it's actually a difference that kind of gets swept under the rug, because later we basically figure out that, hey, you know, the limit of this thing is going to be the same as the limit as a function. And so the function limit is going to be the same thing as the sequence limit. So why do I even care? I just kind of think the function limit will be the same, right? And so we can sort of see that work out here. Now we talk about series. An infinite series is the sum of the terms of an infinite sequence. And the terminology and the notation here is the same as what you used for Riemann sums. So it's the summation notation. So the sigma, capital sigma there, is the sum from 1 to infinity of AK. AK being the terms in the sequence A1, A2, A3, A4, A5. And so you're adding up all the terms in the sequence. And then what we do to find the limit of this, or the value of this sum, is we take the limit of what are called the partial sums. So I add 1 term, 2 terms, 3 terms, and 4 terms, and 5 terms, and n terms, and I get a partial sum of this thing. And then I take the limit of the sequence of partial sums to find the value of the summation. Let me say that one more time. I take the limit of the sequence of partial sums, that is the S1, the S2, the S3, the S4. So as n goes to infinity, where does that go? The limit of that sequence of sums is the total value of the infinite sum. So the infinite sum will have value determined by the limit of the partial sums. Okay. So essentially what we're doing here is we're going to take our infinite sum. We're going to say it's really the limit as n goes to infinity of the partial sum from 1 to n. And then that's a sequence of partial sums that goes to some limit. So this limit at the end here is defined like we define the limit for sequence. And so that is the sequence of partial sums. So let's just look at an example here. So I'm looking at 1 over k times k plus 1. Okay. So what am I going to do here? I'm going to look at partial sums. So I have S1, S2, S3. Let's go to S4. So 1 term in this sequence, so I plug 1 in for k, is going to give me 1 over 2. 2 terms in this sequence is 1 over 2 plus 1 over 6. And 1/2 plus 1/6 is 4/6, which is 2/3. Then I have 1/2 plus 1/6 plus, and then I have plugging in 3, it gives me 1/12. And then again, I add those all up, and what I'm going to get is 3/4. And then I keep going from there. So what I should get is 9/12 out of that. And then I get 1/2 plus 1/6 plus 1/12 plus 1 over 20. And this time it's going to give me 4/5. So it gives me 16 over 20. So this is great. So what I get out of all of this is I end up getting some notion of where this goes. And so if I look at the partial sums, Sn is just going to be n over n plus 1. And so if I take the limit as n goes to infinity of n over n plus 1, what I get is just 1. And here is where we get sort of imprecise, right? So that limit, as I took it, when I think about that limit, I'm thinking about it in terms of real functions. As n gets bigger and bigger and bigger, I have a top and a bottom that are both polynomials. Their exponents are both 1, and then their coefficients in front of them are each 1. So the quotient of these two is going to be the limit, which is just 1. Okay, so that means ultimately this sum is equal to 1. Add up all infinite numbers of the form 1 over k times k plus 1, and I get 1. So that's kind of crazy. It's pretty cool. All right. So finally, the last thing I want to talk about is just sort of a comparison between functions and sequences and series. So sequences and series have an input value of n. Functions have an input value of x. Sequences and series have an output of an, which is a term in the sequence. Functions have an output of f of x, or y. The domain for a sequence and series is integers. So you're only talking 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's all very sort of discrete thing, right? And that's discrete, discrete, meaning there's a nice gap between them, and it's the equal gap between all of them. And then real numbers are input values for functions, and it could be maybe all real numbers bigger than or equal to 1, something like that. The accumulation of a sequence is a series, which is a sum. The accumulation of a function is an integral. The accumulation over a finite interval is the sum from 1 to n of ak, or the integral from 1 to n of f of x. The accumulation over an infinite integral is the infinite sum from 1 to infinity of ak, and then it's going to be the integral from 1 to infinity of f of x. And what I want to maybe mention here, this very last thing here, this and that are very nicely related. So the thing on the left is the sum of an infinite number of things, but it's a discrete infinite number of things, like 1, the first term, second term, third term, fourth term, so on. The thing on the other side is an infinite sum of infinite things. So it's kind of worse. There's a lot more terms in the integral from 1 to infinity than there are in the sum from 1 to infinity. So what's really nice about this is if the infinite integral converges, the sum will also. So if that thing over here is finite, that thing that has a whole lot more terms is finite, then so is the thing that has slightly fewer terms, right? And so that's the idea. So we basically can kind of compare these things and figure out how they are going to relate. And then the other thing I want to mention, the limit of this function is the same as the limit of this sequence. And again, it's the same sort of idea. You have more things that you're taking the limit of here than you are taking in sequences. So if that thing with more things is a convergent and finite, then the thing with fewer is also convergent and finite. And so that's kind of nice. All right. So next time we'll talk about sequences more. And then after that, we'll talk about series more. All right. Thanks so much.